Okay, today we're going to take a look at power series expansions of functions. That is, we want to take a function and write it as a polynomial. Now, we don't know how long that polynomial is going to be, so we're going to let it be infinite. That is, we're going to look at something like f of x, and we're going to write that as a0, some number, and then some number times the x term, and some other number times the x squared term. And we're just going to keep doing that forever and ever. And we could also write this in shorthand notation with the summation formula with an index. So you can see as n equals 0, we get a0 times x to the 0, which is a0. When n equals 1, we get a1 times x to the first. When n equals 2, we get a2 times x squared, etc. So these two formulations are the same. Now the trick is either to pick an f of x and find the a's, or find the a's and pick the a's and find the f of x. We're going to do the latter first. So let's make it real simple. Let's make a0 equals 1, a1 equals 1, a2 equals 1, and in general, a sub n equals 1. So all the coefficients are 1, all these a's. And so we have f of x basically equals 1 plus x squared plus x cubed plus x to the fourth plus dot, dot, dot. That is, all the a's are 1, and so all the coefficients of the powers of x are 1. Now what happens if we multiply this by x? We get x f of x is x plus x squared plus x cubed plus x to the fourth plus x to the fifth plus dot, dot, dot. Now you'll notice the two expressions are almost the same. The only difference really is the 1. So if I take the first expression and I subtract the second expression, the x terms are going to cancel, the x squared terms are going to cancel, the x cubed terms are going to cancel, the x fourth terms are going to cancel, the x fifth terms are going to cancel, and every term is going to cancel. And don't forget, they both go on forever, so there's always a match. So let's take a look at that. That's f of x minus x f of x, and that would equal 1, because that's the only thing that's going to remain when we do that. And now I can factor out the f of x from this expression. And I can solve for f of x. So I now have an expression, 1 over 1 minus x, which is equal to 1 plus x squared plus x cubed plus x to the fourth, etc. Let's just check to see if that makes sense. Let's take a look at 1 over 1 minus x and plug in x equals a half. So this little notation means you're going to evaluate that at x equals a half. Well, that clearly is equal to 1 over 1 minus 1 half, which is the same as 1 divided by 1 half, which is 2. So 1 over 1 minus x at x equals a half is equal to 2. Well, let's take a look at the expression 1 plus 1 half plus 1 half squared plus 1 half cubed plus 1 half. That is, I took that power series expression and I plugged in x equals a half. Now these two things are supposed to be equal. Well, you'll notice that if you take 1 half and add a quarter, you've gone halfway to 1, and then you've gone halfway of what's remaining, and 1/8 is what's remaining, and then 1/16 is what's remaining. That is, I'm thinking of this as a piece of the member line. And then I've got my 1 half, and then what's remaining is a half of that is a quarter, and a half of what that is an eighth. And if I clearly add all that up, I'm going to get 1. So this whole thing is 1 plus 1 which is 2, which is what we got before. Let's try another one. Let's try x equals 1/10. Then I would have 1 over 1 minus a tenth, which of course is 1 over 0.9, which is the same as 10/9, which is the same as 1 and 1/9. And 1/9 is, if you check it, is 1.1111. 1/9 is 0.11111. So this is 1.11111, and it goes on forever. Let's work out the power series version of this. We would have 1 plus 1/10 plus 1/10 squared plus 1/10 cubed plus 1/10 to the 4th, which is 1 plus 1/10 plus 1/100th plus 1/1000th plus 1/10,000th, which is, of course, 1.1111. So it works. So these two expressions are the same. Now, it's harder to evaluate other ones explicitly, but this is the right formula. Give you some confidence that it is. Now, there's something else we can do with this formula, which is kind of clever, which is we have, let's write it out again, 1 over 1 minus x equals 1 plus x squared plus x cubed plus x to the 4th plus dot, dot, dot. Another thing we can do with this formula is we can integrate both sides. Because this is a true statement, the integral has to be a true statement. And we're integrating both sides, we're doing an indefinite integral. We're taking the antiderivative. So we're taking the antiderivative of 1 over 1 minus x. And we're taking the antiderivative of this long sum, which we can do term by term. So what do we get? The antiderivative of 1 over 1 minus x is minus the natural log of 1 minus x. But I better put a c here. And you can check that that's the right answer, because the derivative of natural log is 1 over 1 minus x. And then you use a chain rule, you pick up a minus sign, and that cancels. What do we get on the right side? We get x plus x squared over 2 plus x cubed over 3 plus x fourth over 4, where I'm using the fact that the antiderivative of x to the k is x to the k plus 1 over k plus 1. Okay? Now, that's kind of an interesting formula because I have an expression for the natural log. The problem is that c. But what I'm going to do is plug in x equals 0 on both sides. Let's see what happens. I plug in x equals 0, I get natural log of 1 plus c equals 0, because each of these terms is going to be 0 because I'm plugging in x equals 0. And the natural log of 1, of course, is 0 because it is the power. So I finally get c equals 0, and I have my formula. I'm going to put the minus sign on the other side. Natural log of 1 minus x equals minus x plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 plus dot, 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 dot. And this allows me, for example, to use this polynomial on the right to evaluate various values for natural log of 1 minus x. You have to be careful here. Don't forget, going back to the original expression, the original sum, the sum here, is only good for minus 1 has to be less than x, has to be less than 1, because once x hits 1, this is infinite, or minus 1. You get 1 minus 1 plus 1 minus 1. That doesn't make any sense. So anyway, that's the story, and it shows you how you can play around with these power series expansions and get some very interesting results. The next video, I'm going to show you how to start with a power series expansion where we're going to pick the function and then we're going to figure out what the a's are. All right, I'll see you then.